Recitation problem 2. A mass M1 is connected by a light string that passes over a pulley of mass M3 to a mass M2 sliding on a frictionless surface, as shown in the figure. There is no slippage between the string and the pulley. The pulley has a radius of 25 centimeters and a moment of inertia of 1/2 mr squared. If M1 equals to 4.0 kilograms, M2 equals to 2.0 kilograms, and M3 equal to 4.0 kilograms, then what is the acceleration of the system? The first thing that we need to do for systems of this kind is to complete a free body diagram by representing all the forces acting on the masses as well as the pulley. Here, how the forces are acting on M1, M2, and also the pulley. Let's start with one system at a time. Mass M1 first. M1 is under two forces. The sum of the forces equal M1 times A. Let's detail this equation. There are two forces acting on M1, the tension T1 and the M1G, they equal to M1A. We need to break this one into components, and in order to do so we need to set the system coordinate. Since the object is moving straight down, I'm going to choose the straight down to be my positive y axis, and notice there are no components along the x direction at all. As a result, nothing is going on along the x. However, the y, we have a tension that is pointing negative. Here's your negative T1. Here's the positive M1G. They equal M1A. I can't solve for the acceleration because I don't know what the tension T1 equals. Now we need to try the other mass, M2. M2 is under three forces. Sum of the forces equal M2 times A. There is a tension T2. There is Fn. There is M2G. They all add up to M2A. Let's set the system coordinate for this one. Since M2 is going to move horizontally parallel to the surface towards the right, that's how I'm going to choose my x-axis. The vertical axis is going to be lined up with the Fn. And you make sure you don't mix the system coordinates for M1 and M2. Each one is for its own mass. Break this equation into components. X component, T2 is pointing positive, Fn is 0 because it's vertical, Mg the same way, M2A. Rewrite this equation one more time. T2 equals M2A. This equation cannot help us solve for the A because we don't know what the T2 equals. Notice that the tension T1 and the tension T2 are not equal because the pulley is not massless. Alright, so how many equations do we have so far? We have one here, this is equation 1, and we have a second one. How many unknowns? 3. Acceleration T1 and T2. Where do we get the next equation from? From the sum of the torques acting on the pulley. Alright, since the pulley is going to turn clockwise, for that reason I'm going to use the clockwise as my positive. The sum of the torques acting on the pulley, they equal I alpha. How many torques do we have? We have the torque due to T1 and we have a torque due to T2. We have other forces acting on the axis, which is the center of the pulley, that are all unknowns. Of course they're going to be 0 because the axis of rotation is going to be the center of the pulley. We're ignoring those altogether. Equals I alpha. We need to break this one into components, and the components for torques are interpreted into clockwise and counterclockwise. Since, let's go back to that one. Since the T1 is the one that is turning clockwise, the T1 will have a positive torque, and the T2 is trying to turn counterclockwise. You should have a negative torque. The other thing that you need to notice is the lever arm. Anytime there is a string wrapped around a cylinder is going to be the radius of the cylinder. Torque due to T1 is T1 times R, which is the lever arm, positive because we said it's turning clockwise. The torque due to T2 is negative because it's trying to turn counterclockwise. T2 times the lever arm, which is the radius, equals I, the moment of inertia, which was given to us to equal 1/2 the mass of the pulley, which is m3 times r squared. Alpha, it's known to be, let me write it down on the side, alpha equals the linear acceleration, which is the tangential, divided by r. That's what I'm going to do here. Substitute the alpha by a over r. Notice that this r will cancel with the square. The remaining r will cancel with the r's, which are the lever arms for T1 and T2. This one will cancel with this one, cancel with this one. No r is left in my equation. Therefore, we are reduced to T1 minus T2 equals 1/2 m3 times a. And this is your third equation that includes the acceleration, T1 and T2. This is now my third equation. All we need to do at this point in time is to add the three equations. Notice equation 2 has a positive T2. Equation 3 has negative T2. Equation 3 has a positive T1. However, equation 1 has negative T1, which means if you add the three equations side by side, all the tensions are going to cancel. By adding all three equations, you get m1g, that's from the first equation, is going to equal m1a plus m2a plus 1/2 m3a. Factorize the a from the right hand side of the equation. We will have a times m1 plus m2 plus 1/2 m3. Now to isolate the acceleration, all you need to do is divide both sides of the equation by m1 plus m2 plus 1/2 m3, and the answer for a is going to be m1g divided by m1 plus m2 plus 1/2 m3. Solving for a, we obtain 4.9 meters per second squared.